Hello all, my name is Kyriakos Vamvoudakis and I will talk to you about my NSF Career Award with title Intermittent Learning Framework for Smart and Efficient Cyber-Physical Autonomy. I'm a professor at the Daniel Guggenheim School of Aerospace Engineering and I'm also affiliated with the Institute of Robotics and Intelligent Machines, Decision and Control Laboratory and the Center for Machine Learning. So this is the outline of my brief presentation. So first I will tell you why we want online learning in cyber-physical systems and why continuous learning is not efficient for such systems, and we need to be inspired by behavior psychology, in other words from intermittency, and then develop appropriate learning frameworks for such systems. And then I will talk to you about some preliminary results that we have. So here on the right hand side you see decentralized sensor and actuators that they interact with the physical world, but learning is not happening at every instance, but it's happening based on an intermittent reinforcement scheduling trigger. And of course, since we're not living in an ideal environment, the attackers may actually introduce some erroneous measurements, and that's why we want to protect the whole cyber-physical system. So briefly, why we want online learning? So of course we want to get full autonomy. In other words, we want to design the intelligent agents of the future. So such agents need to operate under unforeseen circumstances, need to realize the first part correct philosophy by allowing equipment plug-and-play functionality, and also to include new data as they learn. And of course they need to interact with others in an intelligent way. And if we can achieve all that, then we can have a significant impact in many applications that are safety critical, such as the ones that the cyber-physical systems. Okay, so of course learning, we need to learn a new task without specifically programmed for that task. So on the left, you see a picture which is taken by David Silver from Google DeepMind, where you can see that reinforcement learning is actually in the middle of lots of fields, including optimal control, machine learning, reward system, classical operant conditioning, where operant conditioning is part of the intermittent protocols that we will talk about, rationality game theory, and operations research. On the right hand side, you see how we can write a control system to actually perform the desired tasks. So whenever I talk about the critic, I mean something that evaluates how good our controller is, and whenever I talk about an actor, is actually the controller. So this is an interesting slide which I borrowed from my friend Peter Mosterman from MathWorks. So here I want to differentiate what is automatic, what is adaptive, and what is autonomous. So as you see, in automatic is the classical observation, action, and through interaction with the environment. Then if we add orientation, then we have added an adaptive part. But autonomy is when something cognitive is added to the appropriate framework. So anytime we add cognition and the reasoning, then we actually can claim autonomy. Okay, so let's talk about why intermittency. So Borges Skimmer, when he was a behaviors professor at Harvard, he indicated that dopamine conveys a single rapidly evolving decision variable in the available reward for investment of effort, and then he called it an operant conditioning. So you can see on the right where you can see a little mouse that actually based on some behaviors, he can get rewarded by food or punished by actually being electrified. So changing dopamine, in other words, immediately altered willingness to work and reinforce preceding action choices by encoding temporal difference reward prediction errors. And of course, this frequency is analogous to the Shannon information criterion. So what Skinner did, he developed the intermittent learning schedule based on time and on behaviors, and can be fixed or variable. So whenever we talk about fixed, we mean that the behavior is rewarded after a set amount of time. Whenever we talk about variable interval schedule, then is when a CPS agent gets reinforcement based on varying and predictable amounts of time. And then similarly, in a fixed ratio, there are a certain number of responses that must occur before the behavior is rewarded. And of course, the distinction in the quality of the performance can help determine which reinforcement method is most appropriate for a particular CPS situation. And of course, finally, in a variable ratio schedule, the number of responses needed for a reward varies. And this is the most powerful type of intermittent reinforcement schedule. So throughout our 5-year award that it was actually awarded this year in May, so we want to actually have the following scientific impact. We want to answer the following questions, in other words. How can we incorporate and fully adapt to totally unknown, dynamic, and uncertain environments? How do we co-design the action intermittent schemes? And how we actually quantify robustness, optimality, and stability, and bring control frameworks to such learning components. And of course, since in cyber physical systems we need to actually solve congestion and guarantee security, we will also try to answer these questions. And of course, we will also develop intermittent deep learning methods that can mitigate sensor and actuator attacks by dynamically isolating those. And of course, we will be able to investigate ways to transfer learning experience among agents that don't have the capabilities of learning. And this will be with ongoing collaboration with KTH, with Carl Johansen, and with Bristol, with Guido Herman. Okay, so these are some preliminary work that we have done. We have developed some intermittent approximate dynamic programming. We were able to actually bring together dynamic and static intermittent and compare the optimal control and the cost from all these techniques. We were able also to extend our frameworks to a containment control where you have followers and multiple leaders, and you want to actually learn different things, not by a continuous framework, but with intermittency. And then, of course, we quantify everything, and we can see on the right-hand side what happens when we have disturbances and when we don't. Another interesting result that comes as a preliminary for this project. So we developed an intermittent Q-learning algorithm to derive optimal policies in a dynamic fashion that can mitigate congestion in an optimal path while learning to avoid problems such as flooding, water leaks, attacks, etc., etc., etc. We introduced metrics of success, and we evaluated this intermittent Q-learning by using anonymized data provided by the Arlington County in Virginia. These actually data are part of a project we have ongoing with the Arlington County. So you see that we differentiate Arlington and the surrounding area in some neighborhoods, and then we wanted actually to avoid the leaks. So the figure on the left is what happens when you don't apply our algorithm, and the figure on the right is when we apply. So you see that with blue we have the neighborhoods that belong to the optimal proposed path that avoids water leaks, attacks, etc., etc. And with red you can see the neighborhoods that they have leaks, okay? And they have suggested to us to actually isolate them from the network. And then we also, since we want our learning mechanisms to be able to guarantee security before they're fed to our learning mechanisms. So what we want to protect them from actuator and sensor attacks, and we're working on actually including moving target defenses. And this is what we call proactive reactive defense. So with the proactive, it's actually classical moving target defense, and the reactive is when we actually isolate the suspicious components. And then with that, I would like to thank you.